Hi, so yeah, I'm talking about today about adding rough paths. So this is a joint project with Carlo, Peter, and Sylvie, and there will also be a thanks to Terry Lyons. So this will be a rough paths talk. So let's first recall what a rough path actually is. So in the geometric setting, so we have a rough path as a kind of functional on the tensor algebra, which is telling us like how to define certain a priori undefined iterated integrals. And abstractly, we write this down as operations on words. So, and we have two algebraic rules. One is the shuffle relation, which is number one here. And the other one, number two, is chance identity. So it tells us that, the concatenation of two pieces of our rough paths is actually the rough path of a full increment. And then we have an analytic condition. And here, for this definition, the big N and the gamma are in relation. So N is actually the integer part of 1 over gamma. Now, speaking of adding rough paths, so first, as I told you, like a rough path gives meaning to iterated integrals of the underlying path, which is in general so irregular that the Steertjes integral on the left-hand side is actually not well defined. And so we do it the other way around. We now use the rough path on the corresponding word to actually define this Steertjes integral. And now the problem is, given two rough paths, if you want now to look at the iterated integrals of the sum, then, well, we expect these iterated integrals to be multilinear, so we can write this out. And, well, the dx1, dx2, the dy1, dy2 terms were well defined through the given two rough paths. But then we have these mixed terms, dx1, dy2, and dy1, dx2, and they won't be defined through these individual rough paths. Now, the solution, like in general rough path theory to this, is a non-unique one. So we actually now need a bigger rough path, which also tells us these mixed terms. And so there's a result that of existence, which is called the Lyons-Victoir theorem, which actually corollary to this shows that for any given two rough paths, with a slight restriction on the gamma, there exists a coupling of these two rough paths, which, well, is a coupling in the sense that if we project down again, so we are now looking at in the tensor algebra of R over R to the 2D. So we have our letters 1 to D, and then here we have another copy of the letters 1 to D, and this is how we embed the original space, the tensor algebra over RD, twice into this, and then the set is supposed to be a coupling. So if we project down to the individual parts, again, it's supposed to be the ingredient, X and Y. But this is highly non-unique. It's just the existence result. And well, once we've fixed such a non-unique coupling, the sum of X and Y can now be defined via simply by a linear map from this tensor algebra over twice the alphabet to the original one, which is shown here. So it's just done in such a way that it really like encodes adding the underlying path components. So this can be done, but you have to fix such a non-unique coupling first. And well, now we come to actually what is the central topic of our project, smooth rough paths. You may now think, what smooth rough paths? Mathematics has gone too far. But actually I will try to make sense of this. So compared to our definition from the beginning, the only thing that changes is the third point. So instead of having this Hölder regularity, we now demand that axis T depends smoothly on S and T. And now this allows us to do very basic calculus again. Like we have a diagonal derivative, which is, as you can see from last representation, is basically you take the path depending just on the T and derive it, and then, well, through this first algebraic condition, we get that this rough path takes values in a Lie group, the character group. And now when we take this derivative via this x to the minus 1 here, we actually pull it back to the underlying Lie algebra of this Lie group. So we now have a nice notion of derivative, which now lies in a Lie algebra. It's no longer a group object, it's an object in an algebra. And an algebra is especially a vector space. So what you can do, you can add stuff. And this is now the thing. Under this smooth assumption, well, why not just add the diagonal derivatives? And this is exactly what we do. So for given smooth rough paths x and y, we now just add the diagonal derivatives. We define this as z dot, and then you can actually show that there's a unique smooth rough path which has exactly this diagonal derivative now. And this is simply like this property from the theory of Lie groups, that for a finite dimensional Lie group, this initial value problem, where you are given a smooth path in the Lie algebra and kind of integrated on the group. But this initial value problem has a unique and global solution. This is something that holds for finite dimensional Lie groups, and it also holds for some infinite dimensional Lie groups, which is then what Milnor calls a regular Lie group. So it's exactly this property when, if we like, we can also formulate it this in like the full, not in a truncated tensor algebra, but in the full tensor algebra. And when we use the property that this will this freely group is a regularly group. And what is our result here is that now with some of rough paths that we have defined simply through the diagonal derivatives has also a nice meaning in terms of like the original rough path, the original rough path increments. And yeah, it's simply like if you have a rough path, a smooth rough path X and a smooth rough path Y, you basically cut them down both to very small pieces, and then you like a zipper, you put one small bit of X and one small bit of Y, one small bit of X again, one small bit of Y again, and yeah, so this statement says this makes sense, and it does not, the increments actually in this smooth setting do not, like if you take an increment of X and attach a little increment of Y, this is approximately the same as the other way around. Yeah, and so we can do this. And the funny thing now with all this smooth rough path stuff, like it's just you can do a lot of the things which are quite involved. Were quite involved in Lyons rough path theory. You can now do by simple derivative calculus. You can just very basically show this by looking at the derivations without like involved rough path stuff like the Sewing lemma or the neoclassical inequality. But actually, if we compare it again to what Lyons did in his 1989 paper, which was a very influential paper, which really kicked off the whole theory. Well, this is where I have to thank Terry, because he, when we talked about my PhD thesis, like he pointed me to this little paragraph in his old paper and said, well, I think this has something to do with your renormalization of rough paths. And we discussed a bit about it, and yeah, it's so that's where really the idea of this adding rough paths and stuff came from, because here now you have kind of the same thing, just that the setting is a bit different. Now we're back into like genuinely rough paths, and we have like basically an arbitrary rough path X, and then Terry found some condition that we are now given another rough path H, which has some much better regularity condition, and then he says he can show that something similar to what I showed to you on the previous slide, that if we put together these increments, the order of like putting them together, it doesn't really matter. It's almost the same asymptotically, and yeah, so this allows us to define here this perturbation. And this is actually what we do in this sum. Just that now it turns out that our smooth rough paths are good enough, just because they are smooth, to fulfill this, very restrictive regularity condition here for H, to fulfill this for any given rough path X. And this leads to a conclusion that actually not only you can, you have a canonical way of adding two smooth rough paths, but also this actually extends to adding a smooth rough path to a genuinely rough path. And so this actually motivates our looking at smooth rough path, because now these smooth rough paths can really be seen as universal perturbations for genuinely rough paths. And universal because it really the condition of it being smooth is so strong that it works for a rough path. It's possible to add it to a rough path of any really low regularity. And finally, as this is a renormalization conference, I also want to say how this is now really connected to renormalization of rough paths, where Terry kind of gave me this hint with his remark, if you look at a time, if you look at a time-space construction where you have given a d-dimensional rough path, and then you kind of add a time component, so a component which is just time t. In this smooth rough path setting, we can write this down very easily now again. It just means, so with x, there's a dot missing, this is supposed to be xtt dot. So this lives in Rd, and when I add this zero, which is not the number zero, but the letter zero, so a combinatorial object in this tensor algebra, if I add this letter zero, then I simply get, this simply defines this time-space rough path via the diagonal derivative. And then if I do translation of rough paths, which is what we call renormalization for rough paths, and choose a translation with an element v0, Lie element v0, which fits in our into our given n, and just define the translation in such a way that it only perturbs the zeroth time component and leaves the other letters invariant, which is to say that it's kind of, that's it's a translation with respect to, with some drift term. When we can simply calculate now this, so we have this algebraic definition of a translated rough path, and when we calculate this simply by the assumptions, we get that the diagonal derivative of the translated thing is just the untranslated set or its diagonal derivative plus with V0 element. And so here the sum comes into play again. So now really we can write this translated path set as the original path set plus a log linear path V, which is just the exponential of this V0 with the time increment. So that's really how this, what also Terry had in mind somehow, that we can actually, how this his old remark of him actually like connects to what we did in 2017 with Lyons-Victoir and Ivar Brunet and also Peter Fritz on translation of rough paths. So, and this was just to motivate you that smooth rough paths are nice. On the one hand, it's a nice toy model for rough paths, and on the other hand, also make kind of sense in the theory as perturbations. Thanks.
Does the setting extend to branched rough paths, or is the smoothness condition somehow imposing weak geometricity?
No, everything that I showed you can do for branched rough paths. The only thing is that in this renormalization setting, this translation operator will no longer be unique based on like these basic conditions. But actually you have an interesting statement that even though it's not unique for this specific translation, it doesn't actually matter which choice you take. But yeah, so with translation it's a bit more involved for branched rough paths, but that's just what was in our old paper about a rough path perspective on renormalization. But besides that, I've just chosen for this talk the weakly geometric case for simplicity. You can do all this for branched rough paths. And also, like, we also looked at even like, you know, more general Hopf algebra setting. How would you think about it? So with some really, this is just needs that you have this Lie group structure, which is true for all rough paths over connected graded Hopf algebras.
I have two questions, I think. The first one would be, can you say something about how the smooth rough paths are like a subset of rough path? I mean, like, how can you, could you say, for example, I mean, ideally, I think you would want something to have like extents or something, like that you can approximate rough path with smooth rough path or so. And the second question would be exactly to that equation there. So you started from your smooth rough path definition, and then basically, if I understand correctly, it boils down to the solvability of this equation. So could you not do the reverse and just say, I start from this equation, and once it's solvable, I can do the things that I want to do, in the sense that smooth is maybe a bit, I mean, if you start from this and you say, once I can solve this equation, I can do what I want. Maybe you can relax in the condition on smoothness of a rough path.
So first to your second question, yes, probably we did smooth for simplicity, but a lot of this, I think, will, like a lot of the theory will already work for C1. and with this equation, I'm actually not sure what the exact conditions are, but I don't think they will be. Yeah, you're right. It's especially in this nipotent Lie group setting, we can write this component like level-wise, and when you see that it's just a linear ODE, so C1 will be fine. Yeah. So that was more for simplicity. To your first question, we haven't really looked at this yet, at the density. Like, I mean, in some sense, you already have this classical result that basically the signatures of just paths, like paths where the iterated integrals are well defined, like that these already lie somehow dense in the rough paths. So you would have, to get some interesting result, you need some maybe refined topology such that, but you really have a nice approximation result, and that is what we didn't do yet.
Quick question, yeah.
Can I ask, perhaps this is naive thinking, so if it is, call me out. I was thinking, suppose you had, I was trying to like implement this, so I had a solution of some differential equation, y driven by w and z driven by x. So we've got a pair of rough paths, w and x, we're going to add them together. Then I can also think about the sum of these y and z. But if I actually think right out the coefficients and expand them just in my head, you don't get the cross terms, which is natural in a way. You would expect the solution is dependent on y and z, or not on some sort of fiddly interaction between them. Do you have an example in mind that is not as nonsense as what I just described, sort of talked about an application of this to a differential equation?
Yeah, for differential equations, you're right. If I just like basically add two differential equations together, then I don't have a problem. But if you want really not like, you're not looking at two separate differential equations and bringing them together, but just want something for which generally depends on which generally comes from, is driven by x plus y in the first place, and you already have some theory for x and some theory for y, then you cannot directly build up the full theory for x plus y.